Okay, I asked you to do this sheet of multiple choice questions just to get you ready for the test. So a charge moves in a circular orbit of radius r due to a uniform magnetic field. The velocity of the charge is doubled. What will happen to the radius? R is equal to mv over qb. If you double the velocity, you should double the radius. So it should be this guy. Inside a solenoid, the magnetic field is definitely not zero, doesn't decrease, doesn't increase, increases and then decreases. No, it's uniform. A proton enters a magnetic field of 10 teslas, and the electric field is 2,000 newtons per coulomb in such a way that it passes through the field undeflected. So this is the equation E equals VB. And it wants to know what's the velocity. So V equals E over B. So 2,000 divided by 10 should give you about 200 meters per second. Which of the following measures will decrease the strength of a magnetic field in a solenoid? So B equals mu O N I over L. I'm going to write it like this just because I don't know what they're going to ask me. Increasing the permeability? Definitely not, because that'll increase the magnetic field. Increasing the temperature, we'll have to come back to that. Increasing the current? Definitely not, that'll make B bigger. Increasing the number of turns, that'll make N bigger. All of these measurements? Definitely not. It has to be the temperature. And lots of times the temperature messes up. Remember we talked about it messes up a ferromagnetic material. It messes up a magnet. It's because it causes the electrons to move into a more chaotic state, and it makes it harder then for things to pass through it, like current or magnetic field. So it has to be increasing the temperature. An electron crosses a perpendicular magnetic field as shown. The direction of the induced magnetic force is, so remember, you put your fingers in the direction of the magnetic field, you put your thumb in the direction that the electron is moving in, the force comes out of the palm of your hand, goes into the page. 3 centimeters from a long straight wire, the magnetic field produced by the current in the wire is determined to be 3 to the negative 5 teslas. What must the current in the wire be? 3 centimeters from a long straight wire. B is equal to mu OI over 2 pi r. And you're looking for I. So I is equal to 2 pi r B over mu O. 2 pi r times 3, whoops, I should have put my number in for r. 3 times 10 to the negative 5 teslas. And it's over 4 pi to the negative 7 Tesla meters per amp. And it says 3 centimeters, so my R is 0.03 of a meter. And when you do this, you get 4.5 amps. Which direction will a compass needle point when it's placed to the left of the conventional current carrying wire as shown? So the current carrying wire is going down, so put your thumb down, curl your fingers. They go into the page here. The compass always points in the same direction as the magnetic field, so it should also go into the page. Turn the page over if I can. Oh, actually, I think I have a second. Number 8. The magnetic field lines determine only the direction of the field, the relative strength of the field, both the relative strength and the direction, only the shape, all of the preceding. It's both the relative strength and the direction. It's not only the shape. If it was just the shape, it could be all of the preceding. Relative strength, because remember, the closer together the field lines, the stronger the field. Can't give us the actual strength, but it can give us relative. And then the direction of the field. A bar magnet is pushed through a flat coil of wire. The induced EMF is greatest when the north pole is pushed through first, the magnet is pushed through quickly, the magnet is pushed through slowly, the south pole is pushed through first, and the magnet rests in the coil. So remember, induced current happens as a result of a changing magnetic field. So the magnet resting in the coils, it can't be that. It doesn't hopefully make any sense to you that it would matter if the North Pole went or the South Pole. You want a field that's changing quickly, right? The bigger the change in the field, the more the current is going to be induced. Number 10, when a loop of wire is turned in a magnetic field, the direction of the induced EMF changes so it's like you have magnets here and you have a loop of wire that you're turning, okay? So so as it's on its way up, the current will be flowing in one direction. And when it's on its way down, the current will be flowing in the other direction. So it's 1/2 up and down, 1/2 a revolution. Number 11, a wire of length 0.15 is passed through a magnetic field with the strength of 0.2 teslas. What must be the velocity of the wire if the EMF is 0.5 volts, 25 volts? EMF is equal to BLV, sine theta, of course, but I think the theta is going to be 90. So the L is 0.15, the field strength is 0.2. It's telling us the EMF is 0.25, and it's asking for the velocity. So V is equal to EMF over BL. So 0.25 volts over B was 0.2 Teslas and 0.15. So on the bottom, it's 0.03 divide 8.3 repeating, I think it is. All right, 12 to 14 are based on the following information. A primary coil of an ideal transformer has 200 turns, while the secondary coil has 50 turns. So NP is 200 and NS is 50. The power generated in the primary, so power primary, is 600 watts. When the coil is connected to voltage primary, is 120 volts. Okay, what is the power generated in the secondary? One would hope it's 600 watts. If you actually wanted to do it, you could find both the V secondary, the I, and the I secondary from the info that we have. And then you could, right, because you could get the I primary. What is the current in the secondary? So now okay, so power primary is equal to V primary, I primary. So I primary is equal to 6,000 watts over 120 volts. I think that's 5 amps. So then I secondary would be I over I primary is equal to N primary over N secondary. Bring your I primary up. So it's going to be 200 over 50 times 5. That's 4 times 5. It should be 20 amps. The induced EMF in the secondary is, I think they put this question in the wrong spot. So V secondary over V primary is equal to N secondary over N primary. Bring the V primary up. It's equal to 50 over 200 times 120 volts. When you do the math, you should get 36, 4 over 3 over 5. Yeah, 10, yeah, 30. Sorry, I was just checking the math there. And then if you went and multiplied these two together, you do get 600 in the earlier one. A loop of wire is rotated 360 degrees across an external magnetic field. During one period of revolution, the EMF in the coil will change. Remember, it's sinusoidal when you rotate it. So it will change in both magnitude and in direction. So it's at the top, positive, and then it goes negative. So it's both magnitude and direction. Done.